Hi everybody, this is lecture 20 and we're entering the third segment of our class. So for everything that we're going to do next, we're going to be integrating functions and vector fields over surfaces. So functions or vector fields over surfaces. And in order to do that, we'll have to be able to parameterize the surfaces. So we already know how to parameterize curves. So here the situation is similar. So let's take a look at this surface that I drew here for you. So it looks like the upper half of a peanut. It's a 2D shape, but it's curved in space. It's a surface. So let's look at this. I want to describe points in the surface with just two numbers, right? So the parameterization of a curve will describe points on the curve using a single number t. Here, I would like to describe points on the surface S using two numbers u and v. So the way this works mathematically is I'm going to introduce new variables u and v, look at the uv plane, and then I want that a certain region of the uv plane, so here is a flat region in the uv plane, I'll call it D. I want that points in this flat region of the UV plane correspond to points in my surface D. So the way I'll describe this correspondence is by a function R, right? Where this function, so it's going to be, it takes two inputs, U and V, and it outputs a point on my surface. That point will have an X coordinate, which depends on U and V, a Y coordinate that depends on U and V, and a Z coordinate that depends on U and V, right? And the parameterization, so the parameterization consists of three functions, X, Y, and Z, in terms of points in the UV plane. But furthermore, it's important that we give bounds for U and V. So in other words, we have to say what's the region where U and V are supposed to vary. So here, U and V belong to a region, to the region D. We'll put that, I guess, we'll just leave it here. Okay, so the point is that as this, so I have, let's go back. So we start with the surface S in 3D space, and then a parameterization consists of a formula for points in this surface S in terms of two parameters U and V. So this means that for every U and V, this point R of UV here, so if I give you a point, a UV here, R of UV lives on the surface for every U and V. I get different points on the surface. And as U and V range in this region D, the corresponding point will cover my surface S exactly once. So I don't want to cover the surface twice. So that'll be clearer in examples. Okay, so let's take a look now at an example of a parameterization. So let's look at surfaces of revolution. So I'm going to show you how to parameterize a whole class of examples, a whole class of surfaces. Well, all right. So here's the setup. We start with a graph in one dimension. I actually would like to move to the next page. So let's start with the graph of a function of a single variable. Here's the graph. Okay, this is a good graph. So y equals f of x. And now we're going to rotate this graph. We're going to get a surface, build a surface out of this graph by rotating it. Let me make it a little bit thicker. But by rotating this graph around the x-axis, right? So let me bring this graph to 3D. Let me draw the z-axis over here. And let me rotate this graph around the x-axis. So here's what I'm doing, rotating it around the x-axis. And what I get will be something like this. here I'll get a really big circle. Here I'll get a smaller circle. Right, and the radius of the circle, the radius of the circle is f of x, right? If I know x, if I give you a number, anyway, if I give you an x value, I'm living on the circle of radius f of x. Okay, so we have to describe, our job is to parameterize this. This is our surface. Our job is to parameterize S. So this means we have to describe points in S just using two numbers. And here I think there is a natural pair of numbers that we'd use to describe points on the surface. So say I want to tell you, I want to describe this point to you. Here's how I could do it. I would say, okay, so this is the point I get by looking at x equal to the value. So if I want to give you this point, I'll just give you its x coordinate. So it's going to be here. So the x value, and then I say it lives on this circle. And the way I got this point was I started with this point, x comma f of x, and then I rotated it to the left. So let me try to draw that. So I'll say I want to describe a point on this surface. Here's how I'll do it. I will say I got the point by starting with some value of x, and here's here's x, f of x, 0, and then z was 0 on the xy plane, and then I rotated it by an angle theta, and then I got the point R that depends on x and theta, right? So we just have to write down. So this is our parameterization, R of x comma theta. Now we have to do a little bit of work to describe, to actually give you a formula for R and theta, but the parameterization it's in our heads now. We know our strategy to describe points. So here's how I'm going to get a point in x. In the surface, I just fix a value of x. This gives me a point in the original graph, and then rotate it by theta. I'm rotating it in the YZ plane. Here's an interesting thing. So I'm rotating. So let me draw the YZ plane over here. So this is, I guess, okay, I should be less careful with the pictures. So here's the YZ plane, and I start with a point, so x here is so at this point over here, y is f of x and z 0. So I'm over here. And then I will rotate it. So I'm going to move on the circle of radius r, and I will rotate by theta and get the point, get another point. So what's this other point? Well, let's use sine and cosine. I'm sorry, the picture is kind of squeezed in there, but this point on the YZ plane has coordinates. Okay, so the distance from the origin, so this distance from the origin is f of x, just like here, and y is f of x cosine theta. Let me just give you coordinates on the original. So here, x fixed. Let's write down the original parameterization. So x, so the point, so we're describing points on our surface in terms of x and theta. So x in terms of x is just itself. Now y in terms of x, if we look at the picture down here, y is just f of x cosine theta, that's y. and z is f of x sine theta. So it's this which is the same as the thing down there. Z is f of x sine theta. Okay, so this is the parameterization, or rather part of the parameterization. We still need another part. We still have to describe the ranges for x and theta. Well, for that I actually needed to tell you in the beginning, which I really didn't. So the picture, the shape, the surface wasn't completely specified at the beginning. So I said it was a surface of revolution that I built out of the graph y equals f of x, but I never told you the ranges for x. So here, let me do that. Retroactively, the ranges for x are a and b, or these values over here. Okay, so so with these ranges, I can just say that x and theta, that x ranges between a and b, and theta ranges between. So if I want to go, full turn, 0, as I drew in the picture, 0 and 2 pi. Okay, if I don't want any repetition, if I really want to cover the surface exactly once, I can use a less than rather than less than or equal to. So in this example, the region D so here are our two parameters, x and theta. So x is between two numbers a and b. Theta is between 0 and 2 pi. So our region D just looks like a rectangle. Right, and the parametrization just moves. So if you give me a point of value of x and a value of theta. So the value I drew over there is kind of like here. Just sends, so the parametrization just maps points like this. Okay. So this is a good first example. We build, so it kind of, I think it brings this example shows you the parameterization is a living, breathing thing, where it's a set of instructions. So in this case, it's a set of instructions to produce a point on the surface. You just say, okay, you move x, so you choose your value of x, look at a point in the original graph, and then rotate by a specified amount. That'll give you a point on the surface, and every point on the surface occurs in this way, right? So I gave you that description, and then we just had to figure out the formulas, for that carried out this recipe. Okay, so next part. So what I would like to do today is to continue giving you a bunch of practical examples like this, which you can use so you can refer to. I want to build some experience with you. So I want to show you a bunch of examples that you can refer to later when you do homework, for example, and you get experience with this stuff. So the next thing I'd like to do is to show you how to parameterize a plane. So the next example is so S this time. So S is the plane through the point 1, 2, 3 with normal vector 1, 1, 1. What I'm going to do here is the recipe. So this is just a specific example of a plane, but the parameterization, the strategy to build the parameterization that I'm going to show you now works for any plane, described like this. If you could just give me a point and tell me the normal to the plane. So let's say here's our plane. and we want the whole plane. Okay, and so I told you, what did I tell you? I told you that the plane contains the point 1, 2, 3, and that the normal vector is 1, 1, 1. So 1, 1, 1 is normal to this plane. Okay. So now let's try. So here's how we parameterize. Here's how we do this. So to build this parametrization, we want to parameterize this plane. To build this parametrization, we're going to find, so the problem is parameterize S. This plane. And so here's the solution. So we're going to start by finding two vectors perpendicular to 1, 1, 1. Okay, so find two vectors perpendicular to 1, 1. Perpendicular to 1, 1, 1. Perpendicular to 1, 1, 1. So let's say the two vectors are, okay, so let's say these two guys, S and T. Okay, so can we think of two vectors perpendicular to 1, 1, 1? So I want, here's our symbols for perpendicularity. So I want that T dot product 1, 1, 1 is 0. And you want that S dot product 1, 1, 1 is 0 as well. Can I think of a T and can I think of an S that do this? And they have to be different. So let's try to find a T and let's try to find an S which do that. So when T times 1, 1, 1 is 0, so this is, maybe I could take here T to be 1, -1, 0. Do you see why? If I do, so if I do this dot product, I'm going to get 1 plus -1 plus 0. That gives me 0 as I want. And now for S, so there are a few possibilities for S. Let me just tell you the possibilities you should avoid that won't work here. So when I say two vectors, I mean, you can't give me the same vector twice, right? I couldn't just say S is 1, -1, -0 again. I also can't just, multiply T by 2 and give you, it's going to be basically the same vector again, right? If I just multiply T by 2, I'm going to get a longer vector that's still perpendicular to 1, 1, 1, but it's not going to look like this picture. We want independent vectors. And surely I don't want S to be the 0 vector. It's not going to look like this picture, and the 0 vector is also a multiple of T, right? It's 0 times T. So here we could take, for example, just use the same strategy, 1, 0, -1, right? It's not a multiple of T, and S dot product 1, 1, 1 still gives me 0. Okay, so I have these two vectors. And now, so with them I can build the parametrization, right? If I have these two vectors, I can find any point on my plane, on this plane. For example, let's say I'm interested in this point over here. It's a point on the plane. I'm going to say, okay, so to get to this point, you start at 1, 1 so you start at 1, 2, 3. And then you add, so then you go a certain amount in the S direction. Then you go here. So let's say, so if I'm building points, let me just write down the parameterization and see if I can explain it. So I'm going to go a certain amount in the S direction, and then I'm going to go a certain amount in the T direction, and that result just gives me the point that I want. So S in our example is 1, 0, -1, and T in our example is 0, 1, -1, 0. Right, so this is the, well, I'm going to write this out as a single vector valued function of u and v, but just let's see if this makes sense. I'm saying that you can get any point on this plane by starting at a point on the plane, a given point on the plane, here 1, 2, 3, and then you move along these two independent, and then by moving different amounts along these two independent directions that are perpendicular to the normal. And if I do that, I can reach any point. So the claim is that this R of uv gives me any possible. If I let u and v vary, I will get any possible point on this plane. And it should be so the point is that S and T here serve as coordinate axes on the plane. So there is a unique choice of u and v that gives me any given point on the plane. So this, I think, is intuitively clear, but if you want, for more, so the best context to think about these things is linear algebra. But here I'm avoiding, I don't want to explore that, even though it's a beautiful subject. It's not the place to explore that further. Okay, so this is our parametrization. It tells us how it's a recipe for finding points in our surface, and gives us all points exactly once. Let me just write it in a familiar formula. Sorry, let me just write it with a single vector here. So it's 1 plus first component is 1 plus u plus v. Second one is 2 plus 0 times u, that goes away, minus v. And then the third component is 3 plus, minus u and then plus 0. Right, so this is our parametrization. So just to stress, the first part is x in terms of u and v. Second part is y in terms of u and v. And the third part is z in terms of u and v. And in this example, let me give myself a little bit of room here. U and v, so the bounds for u and v are that u and v can be any numbers. Or perhaps I should, as I was talking about regions of the plane, the region of the plane in this example is the whole of R2. Right, because I want points at the back here. I want points. So if I want to cover the whole red plane, I need u and v to range over all of R2. All right. Here now I'm moving on to another very useful example. Let's think of a situation where we have a graph, and this is a very common situation. So let's say now another parametrization. Let's say S is the graph of a function of f of x comma y over a region D of the plane. Right, let me draw it here. Okay, I didn't do a very good job. So here's our graph. So S is has equation z equals f of x comma y, right? And x comma y live in D. So D is this region down here of the xy plane. Let me label the axes here. And for this surface, x and y live on the region D. Okay, so this is a very common situation. So normally a surface of a very so the implicit a very common way to describe a surface is implicitly using an equation. I would just say my surface consists of all solutions of the equation, I don't know, x squared plus y squared minus z squared equals 7, right? So I give you an equation and say the surface consists of solutions of that equation. So oftentimes you're able to solve for one of the variables in terms of the other two from the equation, right? Here I was able to write z in terms of, and then what you get in the end is a graph of some function. If you're writing z in terms of x and y, then this means your surface is the graph of the function f. And then the region D is just the projection of your shape onto the xy plane. So this is, so when I mean projection is, so this set, so S is a set of points in 3D. So if I just forget about the z coordinates, set all the z coordinates of all those points in S to 0, I'm going to get points down here. So just by forgetting the z coordinate, I'm going to get a bunch of points in the plane, and that's what I call the projection. So that's to say that the graph this example is very universal. You can typically try to shoehorn a lot of examples. I mean, try to make a lot of examples fill this shape. Okay, so with that being said, how can we parameterize this? How can we describe? So we know, how can we describe points on this graph in terms of two numbers? Well, it turns out it's what you would think. So here it's perhaps so simple as to be confusing. So but the point is, if I know x and y, for, so let's say, I mean, let me try to phrase this as a question. Suppose I know x and y for 2 points on this plane, right? For a point on this. For a point on this graph. Do we know z? Well, yeah, absolutely we know z. Right? So points, so I'll just say, so you see that the points are already given to us in terms of two numbers. So I'll just use those two numbers as my parameters, right? So we'll just say the parameters are x and y, and the point corresponding to x and y is just xy, f of xy, right? This always gives me a point on the graph, and if I tell you that x and y live on this region D down here, I will recover my original shape. This gives me a parameterization of the original shape. All right, let's move on to, this is hard work, but let's move on to another very useful example. So let's look at, in 2D, so when we were doing line integrals, it was very useful to know how to parameterize graphs, lines, and circles. So now we know how to do in 3D parameterize surfaces, which are graphs, surfaces, which are planes, analogous to lines. Now let's look at spheres, which are like circles. So we're going to look at a sphere. So S is the sphere of radius A about the origin. Okay, so A is a number here. Let me just say radius A about the origin. Okay, let me draw the sphere. One of the best, no, not really. Okay, one last try. Please don't be worse than the previous two. Okay, that's a decent looking sphere. Let's look at our sphere, and let me just indicate it lives in three-dimensional space. So we want to describe points on, so that's S, right? And we want to describe points on this sphere. So, and we want to describe these points in terms of two numbers. So in 1D, when we were describing points in the circle, we often, the number we used was often the angle around the origin. right? And when the radius is fixed, and so if you just know the angle around the origin, you know exactly what point you're talking about on the circle. So in spherical coordinates, it's the same, but this time we're going to need two angles to describe points on the sphere, and those two angles we can just use the angles we learned about in spherical when we were working with spherical coordinates. So that's right, to describe points on the sphere, we're going to use spherical coordinates. So those were called theta and phi, right? So if I want to tell you what this point is, just using, so I already know what the distance from the origin is, right? So it's going to be, so the distance from the origin is fixed, it's a. So if I want to know what this point is, I can just tell you what phi is, the angle with the z-axis, so measured from the z-axis, and I can just tell you what theta is, right? Theta is just the angle around the z-axis. So a way to get theta is you just forget about z, and then you get a point in the xy plane, and then you look at the theta angle for that, and that angle measures from so it's an angle around the z-axis, measures from the x-axis towards the y-axis. So the parametrization is going to be, let me recall the formulas for these coordinates in spherical. So the easy one to remember is z. So z is just a times cosine phi. Now there are, so for the harder ones, they're going to be a sine phi. So x is going to be r, so this much, times cosine theta. Now r is a sine phi in spherical, times distance from the origin times sine phi, and then you multiply by cosine theta. And y is going to be a sine phi sine theta. Okay, so this gives us points on this sphere. Now let's look at what about the ranges. This isn't the full parametrization yet. I have to tell you where theta and phi vary. So for this, I'll use the full ranges for both of these angles in spherical coordinates. So that'll be, so I'll just say that theta ranges between 0 and 2 pi, and phi ranges between 0 and pi. And here's this pi. So do remember that we stop one of the angles short of a full turn, just at a half turn, because we want to cover describe all points on the sphere just once. We want the coordinates to describe well, most points on the sphere exactly once. So let's see that this is doing the right job. So let's look at this point over here, and let me take a second. Let me just, so I'll come back to, let me just promise that I'll come back to this, say something else, and then explain that, give you, I think, a clear picture of why I have to stop phi at pi, if that's not clear already. So let's look at that. Let me draw this region, the region D of the phi theta plane. And so it's going to look like this. So the height is pi, and the width is 2 pi. So it's going to look like this. Right, that's the region D in this example. And the parametrization just maps points, in here, to points in the surface, on the surface. Okay, so here's a very useful thing to do when we're trying to check whether the parametrization you wrote down is the correct one. You can ask yourself, what So my claim is that this parametrization is wrapping this rectangle, is just moving this rectangle onto 3D space and wrapping it like paper you would around this ball. Let's see if this is looking right. So if I so let me choose, I don't know, purple and green. So what's happening? So this is a 2D shape. This region D is a 2D shape. It's hard to understand where it goes on the surface. Let me just say, let's look at the constant theta and constant phi lines. So this is the constant theta line, fixed theta, and in green I had the constant phi curve line. Okay, so where does this green line go? So if I fix phi and let theta vary, so I'm on the green line, what I'm getting here on this side, on the sphere side, is a circle. It's a full circle. Right? But on the other hand, if I look at what the parametrization does to the vertical purple line, I'm going to, well, let's see. So we're fixing theta, we're fixing the angle around the z-axis, and so we're fixing theta over here, and we're letting phi increase from 0 to pi. So what I get is this half circle starting from the North Pole and then going all the way to the South Pole. So you see, if I with just these two ranges, if I move this purple arc, if I rotate this purple arc with any possible green angle, any possible angle, I will indeed get every single point on the sphere, right? But if I were using the full range for phi, if I went all the way to 2 pi, then there would be points with two angles. I mean, there would be a point that I would be covering the whole sphere twice. So that's something I want to avoid. All right. So to conclude today's lecture, I'd like to show you how we can answer questions about our surface once we have a parametrization of the surface, right? So we've already seen if I have a surface which is a level set, right, a solution to an equation, we have already seen how using the gradient vector we can parametrize that surface. Sorry, we can find the tangent plane to that surface. This time I'm going to show you how to do the same thing, how to find the tangent plane, but starting not from the implicit, level set description, but rather starting from the explicit parametrization description. And not only this gives us another way to do something we knew how to do, but it's going to be bring us some important ideas. It's going to bring some important ideas to light that we're going to need later. So please pay attention to this discussion. It's important and useful. So let's look at tangent planes. Let's look at this from the perspective of tangent planes. Okay, I think I may wish to get back a picture I drew at the beginning of the lecture. So let me steal this picture here. Okay, so let's say we're interested in the tangent plane at this point over here. So here's what I'm going to do. I'm going to look at the vertical purple line, so the constant u line, and the constant v line. Okay, so the constant u line is mapped to r, to some, not a line, but to a curve, right? Here's the constant u curve on my surface, and the constant v line is mapped to some other green curve. Okay, now here's, so here's an interesting thing. So here I have these two different curves on my surface S, and they meet at the point where I want to compute this gradient. Or sorry, where I want to find the tangent plane. So I'm going to observe this. I can find the tangent planes to this, the tangent lines to these curves, right? So for the green curve, the tangent line is going to look like something like this. Okay, the picture is a little bit cramped, so I'll just do it like this. And for the purple curve, it's going to look something like this. And I can't find that because here's how we compute these. Here's how we find these tangents. So if I want to, so a tangent vector. So one way to get a tangent vector is just to take up the velocity, compute the velocity of the parametrization, right? So here on the purple line, I've fixed u, and then so on this purple curve over here, the parameter is v, which goes up like this, and if I differentiate, so u is fixed and v is changing, so r of u. So r just with u fixed and varying in terms of just varying with v just gives me this green curve, parametrizes this purple curve. So if I differentiate that with respect to with the parameter with respect to v, I get this. I get the velocity vector of this purple curve. And for the green curve, it's the same. So for the green curve, v is fixed, u is changing, and the velocity is dr du. So here I should say, so r of u comma v, as before, is really three functions of u and v put together to form this function with two inputs and three outputs. And so when I write this partial here, I'm just saying take the v partial of x, v partial of y, v partial of z, and put them in the vector. That's this guy. And the other one is with u partials instead. And I should also so here we have, I have to evaluate these partials really at the correct point. So let's say this point here is u0, v0. Right, if the point in the UV plane that corresponds to the point where I want to compute the tangent. So let me just give you the conclusion. So the conclusion is that r sub u cross r sub v, and here let me just give these things their full name. So here I'm really computing the v partial of v. Oh, actually, it's the u partial. R sub u is the u partial at the point at u0, v0. And then I take the cross product with the v partial at that same point. My claim is that this vector is normal to the surface S at the point R of u0, v0. Right, r of u0, v0 is the point on the surface that corresponds. So here, r of u0, v0 is this guy. So it's the point of the surface that corresponds to the point in the UV plane, to this point on the UV plane. So what my claim is that this cross product gives me a normal vector to this surface at this point. And the reason is that, well, yes, this is true because the cross product is perpendicular to both of these vectors. Right, so it's perpendicular to two independent vectors on the surface, and the surface is two-dimensional, so if I have something that's perpendicular to two independent vectors on the surface, it's perpendicular to the whole tangent plane at the surface. And that's what, to be perpendicular to the tangent plane is the same as being perpendicular to I mean, when I say a vector is perpendicular to a surface, I really mean it's perpendicular to the tangent plane of the surface at that point. All right, so this is like the main point. Let me now show you how this works in practice. Let's use this idea to find the tangent plane of a concrete surface. So here the surface is given to us already parametrized. So x in terms of u and v is just u squared. Y in terms of u and v is just v squared. And z in terms of u and v is u plus 2v. And u and v are free. They can be anything. And we want to find, so let me just write this down, u, v belong to R2. So our job is to find the tangent plane at 1, 1, 3. Okay, so as I was explaining in the previous slides, we're going to find this tangent plane, we're going to need to compute this cross product of partials of the parametrization. So I should say, okay, so what's R here? R is just this function. So R in this example is R of uv is, let me cramp it together. So it's just u squared, v squared, u plus 2v. Okay, so with this we can compute the cross product. So to compute cross product, just put the three coordinate vectors on the first line, on the first row. On the second row of the matrix, we enter the components of the first vector here. That's the u partials of R. That gives us 2u, 0, and the u partial of this is just 1. And finally, in the third row, we put the components of the second vector. So the first component, so it's du squared dv, that's 0. Second one is dv squared dv, that's 2v. And the third one is du plus 2v dv, that's 2. So if I compute this cross product, I get I times, the first component is I, I get I times 0 minus 2v. Let me just use ijk notation for change. So I get I times 0 minus 2v, and then j times. So for the j component, you do the determinant backwards, or you introduce a sign, but here I just prefer to use backwards to do it like this. So 0 minus 4u. And then finally we get k times 4uv minus 0. Okay, we still have to figure out one thing. So we found this formula for normal vectors on that gives me normal vectors on my surface. But these formulas depend on u and v, and I don't want all normal vectors on the surface. I just want the normal at the point 1, 1, 3. So I need to figure out u and v so that r of uv, so the corresponding point on the surface is 1, 1, 3. Let's see. So I want these three numbers to be 1, 1, and 3. Can I find u and v that do that? Let's just guess and check. How about, well, I know the answer, but let me just guess the correct answer right away. How about 1 and 1? Well, if u and v are 1 and 1, u squared is 1, v squared is 1, and u plus 2v is 3. So that's what we want. Good. But in any case, this shouldn't be, no, not one, like this. This shouldn't be too hard in practice most of the time. Guessing the right thing or getting it right after 2 or 3 guesses. Okay, so we found u and v that give me that point. So now the normal to the surface. So our conclusion is that the normal at 113, the normal to the surface at 113 is this vector here, n, with components, okay, so it's just this guy, but with u and v both equal to 1, I just get -2. So the first component is -2, and I'm back to bracket notation instead of IJK notation. If u and v are both 1, so I get -2 minus 4, and 4 times 1 times 1, that's 4. So now the equation for the tangent plane at that point at the point 113 is -2 times x minus 1. So sorry, let me just say, so the plane, let me just give you the diverge from the notes and just give you the same answer I gave you last time. So we're going to use -2. Last time we were talking about tangent planes. So we can read off the coefficients of the tangent plane from the normal vector. So they're going to be -2 times x minus 4 times y plus 4 times z. Then it's going to equal something. Now, the thing is, this point 113 lives on the tangent plane, on the plane that's tangent to the surface at that point, right? So I want 113 to be in here. So I want this equation to be true when x is 1. So when x is 1, so let's see what I'm going to put on the right-hand side. When x is 1, I'm going to have -2 times 1 minus 4 times, and if y is 1, I get this, plus 4 times z. At this point, that's 3. So that gives me -4 minus 2 minus 4, that's -6, plus 12, result is 6. So that's what I want to put here. Okay, and this is our answer for this question. The tangent plane through the tangent plane, the plane that is tangent to the surface, to this surface with the given parametrization at the point 113 is just this plane over here. All right, so this is what I had to say today. Thank you so much for listening, and I'll see you guys next time.